Welcome. This is Mark Osborne from PV Tech. I'm the Senior News Editor. I'll be the moderator today. Very pleased to hold this webinar. It's looking at understanding bifacial modules, the true potential. We'll look at the technology innovations and technical bankability, which is obviously a key issue of bifacial PV projects. I have three expert presenters here today. We will be kicking this off with Dr. Lars Podlowski, who is the Director of Global Technical Services at PI Berlin. He's going to kick off with an overview of very much the latest developments that are occurring with bifacial, and give everybody an independent but overall look at where bifacial stands right now. So if you're ready, Lars, over to you.
Yes, hello everyone. Welcome from Berlin. Yeah, I'm happy to be here part of this webinar, and I'm happy to give you about an overview about bifacial PV technology. And what I want to talk about is a little bit about the history of bifacial PV, and then explain to you what are the latest bifacial PV technologies for solar cells and solar modules. But what is most relevant, of course, is to talk about what kind of impact has the system design to the achievable energy gain. A very important aspect is yield prediction software. We will talk about this. And then at the final end, I want to give you some examples of real installations. So start with the history. Actually, the very first solar cell in 1954 already was a bifacial solar cell. And then in the late 90s, when the world's largest solar cell producer was Siemens at that time, their product, Siemens PowerMax, was also bifacial solar cell, but that bifacial feature has not been used. In the past 15 years, there has been a lot of efforts to really promote bifacial PV, and there was like a very early phase of commercialization with some R&D programs and the very first real commercial product from Sanyo, and which then started even more intensive with more companies getting into development and companies building the first specific bifacial technology platforms, which both have happened in Germany, not in Italy, I'm sorry, and also in China. But then since 2017, we really see a third phase of commercialization. There have been large bifacial fields built with the Chinese frontrunner program. A lot of big manufacturers now have bifacial products as part of their portfolio, and it's now discussed to be one of the most attractive options for reducing LCOE. And if you take a look to the forecast, the ITRPV roadmap says that actually in 10 years from now, the majority of solar modules will be bifacial. So this table gives you an overview about the different bifacial solar cell technologies, but I want to talk about only three technologies here today because these are the most relevant technologies from a commercial perspective. One is PERC. PERC is the predominant solar cell technology today, and there's also a bifacial version available. Then the second technology is NPERT, which has been the majority of bifacial products during the first and second phase of commercialization. And then in terms of product efficiency, the heterojunction technology is very interesting. So if we start with PERC, on the left picture, you can see like a standard PERC solar cell, a monofacial version. The dark layer at the rear side is the aluminum layer, and on the right side, you can see like the bifacial version. And what you can see is that just you have to modify the aluminum layer. You have to do openings in the aluminum layer, and then automatically you get a bifacial solar cell. If you take a more closer look, which you can see here, you can see different layers of the emitter and also the local aluminum back surface field on the rear side. But the openings on the rear side make it bifacial. And as you can easily understand, the manufacturing process is very similar to the monofacial PERC technologies. And that's why a lot of companies have been modifying their lines for bifacial version, which has really reduced the cost of bifacial panels a lot in the past years. Nevertheless, the predominant bifacial technology has been NPERT in the past. That NPERT has a better bifacial coefficient because you don't have aluminum on the rear side. So with this kind of technology, you can achieve a bifacial coefficient of higher than 90%. And the best bifacial technology in terms of efficiency and bifacial coefficient offers the heterojunction technology. The cell architecture you can see here, it's a combination of amorphous silicon thin film layers, which has been deposited on an N-type monocrystalline wafers. And yeah, here you can achieve efficiency already, front-side efficiency of about 24%, and the bifacial coefficient, which is higher than 90%. But these products are more expensive because the different manufacturing process requires high investment in equipment. And that's why still today, heterojunction is still some kind of a niche product. Yeah, what is most important, of course, how do the products look like that you can buy? And the majority of the products are basically double glass products based on PPERC solar cell. On the left side, you can see a standard product here. 60 pieces of monocrystalline solar cells, 5 busbar. A big difference to conventional solar modules is the position of the junction boxes. What you can see on the right-hand side is that most bifacial products have 3 small junction boxes which are placed in the outer area of the panel in order to avoid anal partial shading to the rear side. For the double glass panels, you have a rear side, which is 2 to 3 millimeter tempered glass, then an encapsulation material, then the area of solar cells, and a symmetric solar module design actually to the front. There are some more sophisticated or advanced module designs available now. Mostly companies are using now white pattern glass because it improves the front side STC power because some light which hits the spacing of the solar cells gets like rescattered onto the solar cell itself. And this is available now commercially for full-size cells and also for half-size cells. And the example in the middle here is a very specific product. It's a bifacial product, but it's with half-cut cells and with back contact cells. And on the right-hand side, also a product which has been shown publicly on trade shows already, is a bifacial shingled product. But honestly speaking, I'm not sure if this is really commercially available or it has been just shown in order to demonstrate what the future of bifacial modules can look like. What is definitely the presence already of bifacial modules is that they don't have to be double glass. It is possible to substitute the rear glass with a clear backsheet. So in the past years, some very nice clear backsheets have been developed, and this clear backsheet also is available already, as you can see on the lower left-hand graph here with that white printed pattern. So you avoid the loss in STC power, and the predominant or the most popular product now in terms of a bifacial glass backsheet module definitely is the Jinko Swan module. So what is better, glass or glass backsheet? Honestly speaking, I don't know. I think there is not a clear better or worse. So both have their specific applications. Definitely glass backsheet has become more relevant in the past years. Whereas like 2 or 3 years ago, every bifacial panel was a glass backsheet module, but it's good that you have the choice now that for your specific application, you can select what is the best product. So we have to talk about what kind of system design features have an impact to the achievable energy gain. And you see bifacial PV is a very simple concept. There's just light which hits the rear side of the panel, but there are so many additional factors which are driving the energy gain that I listed the most relevant here on the right-hand side. But you see, these are all aspects which do not really influence the energy gain of monofacial systems. So a lot of many more variables, but I want to quickly talk only about the 3 most important things. First is, of course, the albedo, so the ground albedo. What you can see on the left-hand side here is a result of a study from ISC Konstanz, where they have measured the bifacial gain for different ground albedos. And what you can see is that the highest values which are achievable are around 30%, and the lowest values are around 10%. And that is the range that we are talking about. Let's say 10 to 30% energy gain is possible with bifacial systems. And of course, it's important to see what kind of grounds have what kind of albedos. And as you can easily imagine, like white reflective roof coatings or fresh snow have very high albedos. But water, for example, which is maybe interesting to notice, has a very dark albedo. So water is not reflective at all. So some people think using water as a ground for bifacial systems is beneficial, but actually it's really not. A very important factor is the level above ground. So what you can see here is examples of panels which have been installed in different heights, from basically 0 front height up to 0.5 meter. And what you can see, for example, if you look to the light yellow curve here for ground albedo of 56%, if you really place the panel very close to the ground, the additional gain is only 5%. And if you lift it up just 0.5 meter, the energy gain can be up to 15%. So the level above ground is a very important factor that you have to consider if you design a bifacial system. Same is true for row spacing. It's easy to imagine that the bigger the row spacing is, the more light can hit the backside of the panel. There's some kind of a minimum row spacing which you should consider for your system design. The larger the better, but the minimum row spacing should be selected. And the row spacing, of course, is a very important factor for the overall project optimization, not only in terms of technical aspects, but also of financial aspects, because also the area comes as a cost. Yes, there are so many additional factors which are driving the achievable energy gain that yield prediction is much more complicated. And I'm starting here with a statement from Janja Mabray, who has been working at Cypress Creek, now with Peeble. And he's saying well-accepted methodology for energy modeling is the biggest hurdle with bifacial systems. And that's definitely true, because specifically for large ground mount systems, the financing partner has to be convinced. And how you do it, usually through presenting like a yield study. And here's an overview about what kind of softwares do have a bifacial version now. PVSys has a bifacial option since 2017, but also others are available. And it is important that these kind of softwares do get linked to real data. And that's why currently there are a lot of activities globally to verify the accuracy of software tools. I just want to point out like 2 activities here. Like the Department of Energy in the US has given a grant to Peeble so that they can deploy different bifacial and monofacial systems, and they can do comparison studies with different kinds of energy modeling softwares. So I think that's a very important initiative. And also the IEE has an own subtask now for the bifacial modeling. So this initiative is led by Sandia and by Fraunhofer. And this is also very important to get more predictability into the bifacial system design. Some results already have been published. So this is a very recent result which has been published at the workshop just 1 month ago, which has been held in Amsterdam. And here the authors have compared measured data with 3 software tools. And it's interesting that their final conclusion, which is shown here on the right-hand side, saying that bifacial yield modeling is reaching a stage of maturity. So there are definitely like big advances over the past years, and I think it's very important that those studies are made in order to get more financing partners being comfortable with financing bifacial solar systems. Yeah, at the end, I want to show you some real examples. So this is something which you might think this is a perfect condition for bifacial solar farm. It's a flat ground, light soil. This is here in the desert of Arizona. But this is not the only condition where bifacial modules can be deployed very beneficially. So the next example which I want to show you is also a utility scale project, but it's not in Arizona, it's in New Jersey. But also here, like the modeling has shown that it's beneficial to use bifacial panels. Then something which can be very important in the future is like using semi-transparent bifacial panels as some kind of shading structure for agricultural land, so that the agricultural land can have some kind of a double use. So this is from a 6 megawatt field here in Jiangsu in China. And very special applications like vertical fences, also on agricultural land, where a German company has been specialized in. And a very nice application is carports. So what we have here is a very huge carport, 3 megawatt in Qidong in China. At this time where I took the photo, actually the carport was used as a warehouse. But such kind of carports, I would say, is a perfect application for bifacial panels. And bifacial panels can also be installed on roofs. So this is an example from a very large rooftop system. Actually, this is only one building out of many buildings where people have installed bifacial systems on a commercial building which has a wide roofing membrane. And yeah, what you can achieve with bifacial systems is always, again, if you don't do nothing, I would say 5% is something what you can expect. If more than 10% of additional energy is almost achievable for any system, but you have to consider that through in your system design phase. And what is shown here also in the table is that it's very beneficial to combine bifacial modules with a horizontal single axis tracker. Yeah, some kind of a quick summary. I think it's important to know that bifacial PV is not really a new invention. It's just new to a lot of people in the PV industry, and that there have been like two drivers which led to the fact that bifacial PV is becoming mainstream now, which is that P-PERC technology has a bifacial version available, and the cost reduction of N-type wafers is also pushing N-PERT and heterojunction products. The bifacial system design has to consider many more variables, and it's very beneficial to use bifacial panels on a tracker. Yield prediction software is very important to convince finance partners, and most systems now have most softwares have a bifacial option now, and it's very important that they get really verified in the future with real field data. And all these is leading to the conclusion that bifacial offers a large potential for lower LCOE as a very limited technical risk. But of course, you need some kind of experienced engineers who make like a thoughtful system design. Yeah, for everyone who now is really more interested in learning more about bifacial PV, I have two recommendations here. There are a lot of free publications available, so I would like to invite you to download whatever is available on the web. Yes, this was a quick overview about the history of bifacial PV, and so I want to give over to my colleague Stefan from DNV.
Thank you, Lars. Our next speaker is Stéphane Levelised. He's the Senior PV Engineer, Project Engineering at DNV GL, specifically focusing on bifacial technology, and his presentation will cover the bankability aspects, which has been obviously one of the hot topics for bifacial modules for the last couple of years. So over to you, Stéphane. Thank you very much.
Yeah, hello everybody. I was muted, sorry. So yes, we want to talk about bankability improvement for bifacial technology. So we will talk about, of course, some design variables recommended for bifacial technology. Short talk about testing and certification, bankability and modeling, of course. And we will propose very quickly some mitigation and remaining challenges for this technology. So basically, just short definitions, because we often work for lenders, and according to them, bifacial technology is still considered as a new technology. What does it mean? It means for them that if it is a new technology, they anticipate more risk, so they want to get more confidence about project. And when it comes to set up the loan rate and assurance prices, they appoint DNV GL as independent engineer to assess their specific risk. that I have listed below. So as mentioned before, of course, albedo regarding the design to be modified for bifacial technology. We already talked about the ground clearance, which means the level above ground, which is higher compared to the standard technology. Albedo is, of course, something that we have to take care, and depending on the type of the structure, we recommend also to carefully assess also the wind and the snow loads, because the sustainability of the project is also depending on it. And one also recommendation from the NVGL is according to the DC and AC ratio that is recommended to be less than 1.15 compared to, let's say, 1.30 usually admit for standard technology. So of course this DC ratio needs more inverter, but it will boost the energy on output and of course the turnover of the project. Regarding the testing and certification, there are also some improvement to do, because the power evaluation measured in watt peak with the flash tester and the energy output evaluation, what we call the P50 or P90 with the uncertainties, are the main point assessed for the investor and lenders, because the turnover and the bankability of the project is directly dependent of this calculation. So by decreasing the uncertainties, the P90, the technology risk will decrease and the lender confidence will increase. Thus, according to the NVGL, the industry should adopt a standard regarding the rated power measurement, and the modeling and the accuracy of the energy output will be improved accordingly. It is crucial to give more confidence on the technology and improve the overall project bankability. So in few words, bankability is mainly attached to the confidence that lenders have on the project. So it is basically related to a better modeling process. We assume that PVSys is, of course, a software really reliable, but you have to make some modification on it. And of course, we need more data coming from the field to refine the validation and the model. We also propose to everybody some mitigations or initiative, because of course, if we want to, we can ask a lot of things from the technical, but of course there are also maybe some mitigation coming from the investors, and they can probably be more confident now on it. Regarding the main challenges, we list on this slide some challenge still ongoing, of course, regarding the manufacturing. Design, we already talked about it, but there are also big challenges regarding the testing and modeling, and of course all the O&M policies and practices are to be modified for the bifacial technology. So in few words, jumping to the conclusion, of course the NVGL is really convinced that the bifacial technology is a promising technology, and even, as mentioned before, even for 5% gain, it requires significant attention to the design and seating detail, and of course standards and technology are subject to future improvement, and that's the gap between the caution and optimism that defines the current higher business risk climate, and it is what is driving the current push to achieve more predictable and bankable projects. That's all for us.
Thank you, Stefan. So from our side, we go through an introduction about technology and what is achievable and what is feasible and available in the market today in terms of components, modules, bifacial modules in particular, produced by Jinko Solar, which are becoming more and more mainstream. And we see already that even the forecasts presented by different agencies so far are really probably going to be exceeded as normally in this industry. But quickly starting from some facts and figures about Jinko Solar. We are since ever focused on new developments and innovation and new technologies and increasing the performance of the modules to increase the performance of the system and to offer the more advantageous solutions to achieve the most affordable and competitive solutions for the PV industry. So we have achieved different efficiency records, for instance, in terms of cell and modules, which are technologies already used in mass production for our mono-PERC series. For the bifacial solution, the bifacial modules are taking as I said, higher and higher part of the share of the capacity that we have. Today we delivered up to already more than 40 gigawatt of modules, with the capacity expected for this year up to 16 gigawatt. And out of that, potentially with the new technologies implemented, virtually all of it might be even bifacially if needed. Of course, we are increasing flexibility at production level to achieve that if needed, but for sure, the trend is really to increase more and more the market share also on the bifacial technology. Looking at the portfolio, for instance, we see how nowadays, even in our portfolio, the bifacial solutions with the two versions, for instance, with the double glass structure and glass transparent backsheet structure, is occupying a significant high portion of capacity, and that's also because of course the demand is increasing, especially for utility scale projects. We see a lot of customers really very active and allocating a significant amount of pipelines on bifacial systems and bifacial solutions. It is of course possible to achieve bifacial modules, to produce bifacial modules based on very mature and reliable technologies used already in the past in previous series. As Lars was presenting before, our technology, for instance, is based on P-type silicon based on PERC technology, so a mature cell technology made bifacial and then combined into a bifacial module, still based on the larger cheetah type cell dimension with an efficiency up to 22.3% on the front side, and potential power at module level, including front and rear, up to 500 watts in total, depending on the of course on the albedo and on the setup that we have at the bifacial system. Also, bifacial modules comes with a longer warranty and expected lifetime because of the material used, because of the structure that we will see later, makes them very durable and reliable. That's also another benefit that we have at system level to make the PV systems work longer and more efficiently, reducing the LCOE ultimately. We can have, of course, thanks to the rear of the module, a power gain up to 25 or even 30%, as we saw in the previous presentation from PI Berlin, and that's achievable, of course, depending on the design and the construction of the system. But clearly, figures that we will see later on in the presentation, confirmed by different test sites that also from our side we are developing and analyzing to make sure that those figures are not only simulated values but real measured values, to make the technology comfortably bankable in the end. The advantage of having, for instance, bifacial module with a front side with glass and the rear made of polymer, made of transparent backsheet, is different for different reasons. One of them, for instance, is that it can be lighter. It is lighter, 25% lighter. And that's directly impact the BOS cost, the labor cost, the installation cost. So the energies and resources we need to install the modules are reduced, leading directly to a benefit at costs reduction for the construction of the PV system. Another effect is on the construction of the mounting system on the hardware, because being lighter, of course, we need also somehow lighter mounting structures. We don't have to use extra reinforcements or extra metal to make the trackers or racks more robust to withstand the load of the bifacial modules with the Duraglass. And thanks to the framed structure of the modules, that makes them compatible with any traditional or standard mounting structures that we can find available in the industry. And that's also somehow giving an advantage on installation costs, because glass modules, especially with the frameless version, require special clamps, which makes installation more complex and also more expensive. In terms of reliability, as I mentioned, the bifacial modules in both versions are expected to have a longer lifetime, and that's confirmed by analysis done by the supplier of the basic material that we use for especially for the bifacial modules with the transparent backsheet, which is DuPont. In this case, all our transparent backsheet bifacial Swan modules are using a Tedlar material at the outer layer of the backsheet, which is the most durable that can be used for PV modules. And that's confirmed, for instance, in this graph at an exposure against UV light, which is simulating a 30-year exposure in a desert area. And we see that the reduction in mechanical properties on the right-hand side and in optical properties on the left-hand side are confirmed to be stable and not degrading over the 30 year of life expected for these models, which is, of course, very important to make the technology reliable, bankable, and to have, of course, confidently investors use the technology. That's also confirmed on the site, on PV sites, real sites designed and constructed with this material, the transparent backsheet, Tedlar-based material, which have been put on installations already more than 20 years ago and tested and monitored, and to confirm that even in the real, not only in the laboratory but simulated environment, but also in real installation, in real environment, the modules are stable and durable. So that's what happened, and that was confirmed thanks to this demo installation in this case, but real installation. That was confirmed that really the properties of transparency and mechanical properties of the material are stable as shown before. We saw already in the previous presentation how high can be the power gain that can be achieved with a bifacial module and a bifacial system. We confirmed that also internally, measuring that directly in our test sites. Our R&D team is also investigated the potential of bifacial a lot to make sure that they are used and installed in the optimal way to maximize the performance of the modules and the system. We see that we range in different scenarios between the 5% and 20% roughly power gain, realistically achievable according to the setup that we have in the different conditions. Thanks to this general range data, we set up some demo installations to measure practically the real power gain, the real increase that we have on production thanks to the bifacial technology. So not only to rely on simulations or theoretical data, but really to validate instead, to confirm that those numbers are actual numbers we can use to define even business plans in the end. So this one, for instance, is the first case study that we analyzed with the maximum albedo possible with a completely white paint background. In this case, the albedo, of course, is the maximum possible. It can be even higher, probably in a better optimization of system setup. But in this case, we see that in some moments the installation was really achieving that 20% we were talking about, 20% power gain in terms of energy generated by the rear of the PV module. A more common situation with a sand background, for instance, still based on a mounting system using fixed structure. Also in this case, the power gain is well in line with the estimated values, actually slightly above the numbers that you can probably achieve with PV-cyst in general, which is probably a little conservative, but that's a reason why we wanted to validate, to confirm that the power gain and the energy gain can be practically be achieved in a real scenario. In this case, we have used Swan bifacial modules with transparent backsheet, so also to practically test on ground on real installation, that technology we talked about before in the presentation. We see that the power gain is between 10 and 12% compared to the bound-on facial module, and this was the case with, as I said, a sand background and a fixed mounting structure. Changing the background, in this case moving to a green field, so grass in this case, the power gain is, of course, as expected, slightly lower. So we know that the albedo of grass is lower compared to sand. In some cases, of course, sand can achieve a much higher albedo and much higher power gain, as we shown before. But the interesting thing of this case study in particular is how obvious is the proportional gain that we have during winter time. So for instance, a period where albedo is proportionally much higher compared to direct light, of course, depending on location, can be much different. But in this case, the power gain in January, for instance, was targeting really the 15% even. So in this case, it's an interesting analysis of how an interesting reference on how beneficial and profitable can be bifacial technologies and solutions, even in location where there is not much direct light, or let's say better, there is more proportionally more diffuse light and more albedo light than direct light. So talking about Northern Europe, for instance, or places where direct light is not so strong as Southern Europe installations, or other regions more affected by direct light intensity. Another case, moving to tracking systems. So in this case, of course, the power gain is going up because we combine the bifacial plus and tracking systems solution with the two combinations shown before. So grass, in this case, the power gain was above 12%. It is interesting to see in this case how is important the season variation that we have in terms of color of the ground when we have a natural green field, for instance. We know that, for instance, in autumn, the color change in the grass leads to a proportional change in the power gain. So that's also positive, and then we see that how strong is the impact of the seasonal change and the color of the ground to influence the albedo. And that, of course, has to be taken into account because it increases the complexity of the estimation month over month on the bifacial system in case of this kind of installation. More constant power gain we have instead on sand background, also combined with tracking systems, because in this case, of course, there is no seasonal variation basically, unless of humidity change of the ground, but more or less stable throughout the year. Of course, in this case, as in the previous analysis, the installations were monitored for the first part of 2019. So of course, we don't have the complete yet data for the full year, but we have enough data to estimate more or less what will be duplicated also in the second part of the year, somehow symmetrically on the other side. We want to conclude then our presentation talking about a practical business case study, just to have just to give an idea about how figures in terms of financial aspects can be different, simulating a business plan, for instance, for a bifacial module compared to a monofacial, bifacial systems compared to a monofacial system. In this case, we wanted to take a utility scale project of 100 megawatt size, with an estimated capex of 70 millions, for instance, and of course a given cost for operation and maintenance throughout the 25 years. In this case, we assumed a very high radiance location, about 1500 kilowatt hour per square meter annual radiance, with a general PR for a normal PV system, achievable realistically in the field. So we achieved almost 3 million megawatt hours during the 25 years operation of the PV system, and let's see how those figures combined to the different solution can lead to an estimation, a rough estimation of LCOE in the end, and how it can be comparing the two options influencing the LCOE level in the end of the bifacial solution. In the first case, on the left hand side, you have the comparison of the monofacial module and the monofacial system, which gives an LCOE of around $25 per megawatt hours. Of course, can be probably ambitious or difficult to achieve in some locations, but in many locations, Southern Europe, for instance, with a very high radiance and relatively low costs of installations and maintenance operations, then can be somehow achieved. On the right hand side, if we increase by, for instance, realistically 10% the performance and the generation of the PV system, thanks to the bifacial design of the PV installation, and then also considering the lower annual degradation of the module nominally, then we increase significantly, of course, the energy generation of the system, and we can see how even if we have higher total expenditures, of course, because of the higher cost for some components like modules or mounting structures somehow, or lens if we have to increase the ground coverage ratio. Also in this case, we can reduce the LCOE, and roughly a 5 or 6% reduction on LCOE is realistically achievable thanks to the extra generation in energy of the PV modules and the PV system in general. Not considering in this case, for instance, even the extended lifetime expected for the modules. So in this case, the simulation was ended at 25 years. But of course, if we increase that lifetime of the systems up to 30, then of course the reduction in LCOE is achievable is even higher. So to summarize, we can, with a bifacial system, achieve an energy generation higher energy generation up to 25 or even 30% in very optimized PV design and PV systems constructions. With the with the transparent backsheet version Swan bifacial module from Jinko, of course, you can have a lighter module by 25%, which is reducing proportionally up to 20% the module installations and labor costs. So therefore giving an advantage at BOS cost level, and ultimately allowing for a very significant LCOE reduction, even though components might be slightly more expensive in some cases. Still, the reduction in LCOE is realistically achievable, as presented in the business case that we shown in this presentation, and quantifiable in really up to 5 or 6% over the total lifetime of the system. Thank you very much. To you back, Mark.
Thank you, Andrea. Andrea Viaro is the Head of Technical Services of Europe for Jinko Solar. Thank you very much for that, Andrea. Right, we've got a good nearly 15 minutes for some Q&A. Just want to let everybody know that the presentations will be available. We have to obviously process those, but they're normally up in the next roughly about 10 days from now. But we'll probably send a notification out highlighting where they are and that the presentations will be available. Another aspect is that you can use info@pv-tech.org and you can send questions to that mailing address, and we can forward those to the relevant people as well. There has been a lot of questions, so we're not going to get that far through them, but certainly if I would like to start off with and ask Lars a couple of questions. A lot of people are obviously talking about what's the best ground surface, what's the most cost-effective ground surface to use for albedo, but I think there's a misconception going on here with some of the attendees that other than very low or high absorbing ground surfaces, like as you mentioned, Lars, water, there is plenty of light hitting the backside of a wafer and on the cells. So just maybe give sort of an understanding of that to people, that it's not just coming from the ground surface.
No, it's not actually. I've shown in one of the graphics that, of course, there's also light coming like from the sky, like scattered, like indirect light, which gets scattered from clouds. And the albedo, of course, is a relevant factor, but it's not the only factor. For example, it's very beneficial for bifacial systems to use a higher tilt angle of the panel so that really more light can hit the backside of the panel. So it's even if you have like a fairly low ground albedo, you should definitely consider a bifacial panel. What I've known from a few projects is that it doesn't make sense to really like modify the ground with white gravel or so. Usually the additional costs that are related to such kind of measures do not pay back. So use the ground that you have and then try to optimize your system for that specific ground.
Great. Another question for you, Lars, relates to, obviously, we didn't discuss this particularly, but the potential for mismatch with bifacial modules, due to the nuances of the technology and all of the ways in which scattered light, etc., occur. What's your take on that?
So there is definitely mismatch, and also the risk of mismatch is higher than with monofacial systems. So the biggest mismatch you can see at the end of rows. If you have like large tables for ground mount systems, at the end of the rows, the panels do not have a neighbor, and they really see more light. So there are some studies. If you go to all the presentations from the bifacial workshops of the last years, there are a lot of presentations about the inhomogeneity of irradiance on the rear side and the mismatch of panels. And it can be beneficial to use power optimizers for such panels, specifically at the end. So that's definitely something to consider.
Okay, thank you. A question for Stefan, if you wouldn't mind. We mentioned obviously the performance ratios and the way in which bankability is assessed, but I think there was a question. I'm just trying to make sure I read that out correctly. People are talking about several questions all in one, really, but how to correctly measure the capacity of a PV power plant with obviously bifacial modules. It says here, in an unbiased manner, but I think everyone pretty much knows that everyone is trying to provide real data so that all of the types of software available become increasingly accurate, and then it's just simply down to a choice of what type of software you're going to use for your bankability. But maybe you have a few points on that, Stefan.
Yes, so of course PVSys is a really accurate software, except that you must, for the bifacial module, adapt slightly the tool and take into account, of course, the bifaciality. So for example, we developed in GNVGL a tool to assume what will be and depending on the albedo, bifaciality ratio, etc. We have a tool that help us and that support the energy output calculation. Of course, we also work with PVL laboratory, for example, and Jinko is a very good example of that. We have on-field measurement, and we have also our independent pan file, just to make sure that depending on the temperature, etc., the pan file is the best one. And then putting everything together in PVSys, we have a very good calculation of the P50, and of course after that the P90 level.
Right. Yeah, because there's a related question going back to is there a standard albedo that would be used for your reference to that 1.15 DC to AC ratio? And I think another question which is related in many ways is how can a bifacial string be tested on site during commissioning or later, or what would be the preferred route to that?
Yeah, so that's why we recommend to have a lower DC ratio to take into account the albedo effect, the bifaciality ratio, etc. So this is, as usual, a recommendation, but sometimes we will recommend, or we will, let's say, have no remark regarding a DC-AC ratio with 1.2, depending on the project. The most important for that is we assess the bankability. For the bankability, we assess a project per project. We don't have, let's say, a generic answer for that. So we look carefully at the data, how the albedo is calculated, etc., etc., and what is the electrical design, etc., etc., just to make sure that the DC-AC ratio is well calculated. And but in general, we recommend to have to take into account the higher current. We recommend to have a lower DC-AC ratio for bifacial project. That's one big difference compared to the standard technology.
A question for Andrea, if you don't mind. Obviously, there's been a lot of questions asking specifics, especially around the data that you presented from the different sites, as to whether Jinko was making that kind of information publicly available to the software companies. But I do know that a lot of companies are now starting to provide that because they realise it's a win-win situation. But I didn't know whether you could say anything specifically on that point, Andrea.
Sure, Mark. That's a very good point, because as I mentioned during my speech as well, the validation of the simulation systems are crucial to make sure that the numbers coming out from software are accurate and realistically matching with what would be actually the real performance of the system in the field. We are working on different aspects, of course, using our internal data to publish even a white paper which should be released soon. Probably we will include also some of the figures also in that document. Working with also even the mounting systems suppliers to understand how to optimize the combination of modules and trackers. That's also a discussion that we want to bring ahead also with inverters manufacturers, to make sure that the complete system will be really performing in the best possible way. And then, of course, down to simulation software, PVSys is only one of them, of course, but we are opening discussions with others that were mentioned or also during the presentations presented today, because, as I mentioned, the validity of the simulations are really, if related to a real validation or confirmation of the numbers. Of course, we don't want to bias or somehow influence the numbers, but clearly our purpose is really to make sure that the modules are the technology is understood and confidently considered bankable. And to achieve that, we really need to work together with the other partners of the BOS of the systems, and with also the simulation tools developers.
Excellent, thank you. If I can keep you on there, Andrea, just one quick question to you and one quick answer, if you don't mind. Although it's quite difficult. Actually, I've just been told now we're going to run out of space, run out of time. But just to reiterate to people, if you can use info@pv-tech.org, and we can ask for questions. Obviously, we haven't got time to fit into the webinar, but we will pass those questions on to the relevant people. And just to kind of say thank you to our 3 presenters today, and thank you for everybody that attended this webinar. Thank you. Bye-bye.